Thank you. Good morning. First, two things that we saw yesterday. I forgot. I wanted to talk about absorption, neutrino absorption. We have seen that the cross-section on dimensional ground must be proportional to the square of the Fermi constant and to the mass squared in the center of mass frame, and S is of the order of ME. M is the target, is the mass of the target particle, and E the neutrino energy. So if we, let's say, substitute for the Fermi constant about 10 to the minus 5 GeV squared, and so multiply and divide here, and measure the target mass in GeV and also the neutrino energy in GeV. This is about, okay, so 10 to the minus 10. And here we have this and this cancelled. So M over E in GeV squared. And then we use, to go from GeV to, so we have here 197 MeV per Fermi squared divided GeV squared, and this is 10 to the minus 10 about ME divided GeV squared. This is 10 to the fourth, let's say. Then we have here 10 to the minus 6, and Fermi is 10 to the minus 13 centimeters squared, and so we get 26, 32, 42, minus 4, the 10 to the minus 38 centimeters squared, the factor that yesterday I wrote on the blackboard. Now, from the cross-section, you can get an estimate for the mean free neutrino path, multiplying times the density of the target of mass m. And for ordinary matter, you have that this is around roughly the Avogadro's number, and so this is like, let's say, 10 to the 24, 10 to the minus 38, and this is centimeter cubed to the minus 3, centimeter squared, so this is in centimeter. So roughly 10 to 14 for target mass of 1 GeV when the neutrino energy is of 1 GeV. So in kilometers, this would be okay, centimeters, so 2, 3, 10 to 9 kilometers when the neutrino energy is 1 GeV in the Earth. Okay, so the mass of the nucleon is 1 GeV. If you consider that the diameter of the Earth is of the order of 10 to the 4th kilometers, you see that neutrino are absorbed when the energy is of the order of 10 to the 5 GeV. Lower energy, the Earth is nearly transparent to neutrinos. Same thing with respect to the Sun. But when you go into, for instance, a neutron star, in the case of an exploding supernova, the density can be of the order of 10 to the 12 times the Avogadro's numbers. And the mean free path for a neutrino is of the order of 100 or 1000 meters. And so a neutrino sphere is formed because neutrinos are trapped for a few seconds. Okay, so this was what I forgot to say yesterday. Then I realized also that I make some, not really a mistake, but a problem with the convention for the neutrino mixing, because we saw that the neutrino mixing can be written as the product of 3 rotations, and but I consider as a rotation in 2 dimensions a matrix cos theta minus sine theta, cos theta. Now, this is a rotation. For instance, consider this arrow. This is the plane, x, y. If you rotate the arrow by an angle theta in anti-clockwise direction, you get this rotation matrix for the components of the this point P. But you have always 2 ways of considering a rotation. You can rotate the physical system, in this case the point P, or the frame of reference. So if you rotate the frame in anti-clockwise direction, this is equivalent to rotating the point P in clockwise way. So, and this is the convention of the PDG, the rotation matrix is this one with theta going into minus theta. So the minus is down here. Okay? So with respect to yesterday, the convention for the mixing matrix is this one, not this one. This is the way I remember a rotation. Okay. And so now we can continue with the mixing matrix. We saw that U is the R23 rotation times gamma delta R13 theta 13 gamma delta dagger and R12 theta 12. So these 3 matrices are simply the extension in 3 dimensions of a rotation in a plane. Okay. While this gamma delta is 1, 1, 0 everywhere, e to the I delta. In the case of Majorana neutrinos, let's say Majorana neutrinos, the mixing matrix is U, the same U, times 1 e to the I phi 1, e to the I phi 2. Okay, but we will see that in the case of neutrino oscillations, these two phases never appear. So only for a given class of experiments the Majorana phases are important, but not for oscillations. Now we want to derive, in the case of vacuum, the formula for neutrino oscillations. Remember that we have defined, in the case of fields, the flavor fields as rotation, let's say through the mixing matrix, a combination, linear combination of the mass eigenstates. Now, if you consider a neutrino state, so a ket vector, the relations between the flavor eigenstates and the mass eigenstates is through the U complex conjugate. Because if you remember the Fourier expansion of a spinor, the 3p 2 pi 3 half square root m EP sum over S U PS B PS e to the minus I P dot x plus V PS d dagger PS e to the I P dot x, you see that this is, for instance, the field for neutrino. For a neutrino, the field nu contains the annihilation operator for a neutrino and creation operator for an antineutrino. So if you want a neutrino state, you have to use psi bar. And so the relation between a flavor eigenstates and a mass eigenstates, let's say, okay, 0, is through the complex conjugate. Sorry. This is when you consider the. Your question is why I. This is the Fourier expansion of a Dirac field. No, what I said is why here you have. This is how the Dirac field is. So when you consider psi on the vacuum, this part gives 0 because this annihilates the vacuum, and this creates an antineutrino. If you want neutrino state, you have to use psi bar on the vacuum. Okay, so that you here have B dagger and here D. So annihilate an antineutrino. Okay, is the standard, let's say, Dirac field. Okay, but is this clear? Sorry. Are you right with this? Okay, but this is. Okay, the name changes. In Italy, we like B and D. No, I use the. Okay. You can. For a Dirac field, you need two names. Okay, because you have to distinguish particle from antiparticle. For photons, you have A dagger. okay? And moreover, there is a real field, the electromagnetic field. But for a fermion, you need two different operators. You can call whatever, how the names change. I use the Bjork-Andrell convention. It was a book for from the 60s, because I'm slightly older than you. Okay, but this is just the name. Maybe there are many books that call in another way. Okay, so I use B for particles, D for antiparticles. This is just the definition. Sorry, I was thinking that your question was different. Now, there is another potential source of confusion, because you can have, let's say, a neutrino state, and you can write it as a superposition of flavor eigenstates. So alpha, E, mu, tau, let's say nu alpha, so these are complex numbers. Now, if you, so this is fields, this is for fields, states, and let's see components. Now, you want to understand how this transforms when you can write a given state, ket, also as a superposition of mass eigenstates. Okay, so nu1, nu2, and nu3. So we consider the flavor eigenstates, nu e, the ket, nu mu, and nu tau, and the mass eigenstate, nu1, nu2, and nu3. Now, just by inserting the identity, so sum over alpha this is the identity, or the sum over I for 1, 2, 3, so this is by definition the identity. If you insert here the identity, you can prove that the components will transform again like fields. Okay, so typically this is what we use when we discuss oscillations. And so instead of U star, another time it will appear U. Okay, so this is not always very clear when you read some book or article on neutrinos. Okay, now, what are neutrino oscillations? From a conceptual point of view, it is not difficult to understand that when a neutrino is produced, yesterday we saw the charge current term. So a charged lepton goes into a neutrino, and the W is in the vertex, the third particle. So a flavor eigenstate is produced by an interaction. But when a flavor eigenstate is a superposition of mass eigenstates, and the mass eigenstates are the states that have definite free momentum or velocity. So when a neutrino is produced, it is a given combination of the mass eigenstates, depending on the mixing matrix. But when neutrino propagates, mass eigenstates are the ones that have definite free momentum. So at the detection point, in general, the superposition of mass eigenstate will be changed. And so the probability of detecting a neutrino of different flavor from the initial one is not zero. This is the oscillation let's say, phenomenon. Okay, is a typical quantum mechanical process depending on the mixing. Now, we will often use this approximation. So the neutrino energy, so consider a mass eigenstate, and the energy of this neutrino mass eigenstate is the square root of the sum of the mass squared of the neutrino, and this is actually the modulus of the 3 momentum squared. Okay, that and we know a posteriori that neutrino masses are very small, so we can so here I used P to say the modulus of the 3 momentum. So 1 plus mi squared divided pi squared, and this is roughly pi times 1 plus mi squared divided by 2 pi squared. And since masses are very small, we will always do what is called the equal momentum approximation. So we will use P for all mass eigenstates, that is approximately the same, and to the same approximation order, here we can put P, and so we will write P plus mi squared also to E. So 1p simplifies, and neglecting term of the order of mi squared divided p squared, we can trade p for E. Okay, in the oscillation formula, this is an approximation that we will use. Now, this approximation allows us to derive the oscillation formula more easily. The right way to do the computation would be to use a wave packet treatment, and so in a way that is much more complicated to derive the oscillation probability. But in the end, the result is the same. So with this approximation, we are interested in calculating, for instance, the probability that a neutrino that initially is of flavor alpha, after a distance L, is detected with flavor beta. Okay. Another approximation that we will use is that the time is equal to the length. So the speed of light of neutrino, the speed of neutrino is the speed of light. And this is a good approximation to the same order, neglecting this. Now imagine that for a neutrino of 1 GeV, this is of the order of 0.1 EV divided 1 GeV squared. You see that this is a very good approximation. Also for MEV or KEV neutrinos. Now, this is the modulus squared of, let's say, nu beta and nu alpha L, where this is for us the, let's say, the state alpha produced as in flavor alpha initially after a distance L, modulus squared. But we saw that the eigenstate of the propagation, the free Hamiltonian, are the mass eigenstates. So we can write this as sum over I and j u beta j u star alpha I nu j nu I L modulus squared. So what we do, we write the states in the flavor basis as a superposition of the mass eigenstates. So there is a u star when you expand this nu alpha. So nu alpha is the sum over I of u star alpha I nu I L. And the same thing for nu beta, but this is a bra. So there is another star. So twice the complex conjugation gives back the u. Now we can write what these states are, because a mass eigenstates during propagation simply gets the phase e to the minus I e t, or L. Okay, so this is equal to the modulus sum I and j from 1 to 3 u beta j u star alpha I, let's say nu j e to the minus I ei times L nu I squared. So the Hamiltonian in the mass basis is diagonal, okay? And so after a distance L, if you start with the mass eigenstate nu I, you get simply this phase. This would be T or L, it is the same. Now this is just a number, goes in front, and this will give delta. And then we use this approximation, okay? So here we replace EI with P plus MI squared divided 2E. So the energy for all three mass eigenstates can be considered the same to this order of approximation. And so we get, let's write e to the minus I p L. This nu j nu I is simply a delta ij, and so one of the sum can be simplified. Let's say sum over j, and we get u beta I u star alpha I e to the minus I L mi squared divided 2e modulus squared. Okay, so imagine to replace E with this one. This P is the same for all neutrino, goes in front, P times L, and can be cancelled because we want to make the modulus squared, and this is just modulus 1 number. This index was J, but now is I. And so we end up with this expression. And if you have a complex number and you want the modulus, you take the number and multiply times the complex conjugate. So we end up with, let's say, sum over I and j again, because we multiply this sum over I times the sum over j, and we get u star alpha I, u star beta I, u alpha j, u star beta j, times e to the minus il. You see, here the complex conjugate will give the same product with index j, and the star here, and this is just u, and so this product of 4 terms here, minus il divided to e, and then mi squared minus mj squared. Okay, so the minus comes from the complex conjugate. And this is our final formula. Sum over I and j, u star alpha I, u beta I, u alpha j, u star beta j, e to the minus I, L, let's say, delta mij squared L over 2e, where this delta ij is mi squared minus mj squared. So this is the simplest way to derive the vacuum oscillation probability in the so-called equal momentum approximation, but nevertheless the result is correct, and for the moment we notice that the oscillation probability, so probability of finding the flavor beta at a distance L when an alpha, neutrino alpha, initial flavor eigenstates was produced, depends on this combination of the matrix U mixing matrix elements and on the distance, the path, the neutrino initial energy, and on the difference of the mass squared, not on the every single mass, but the difference of the mass squared. So, since we have 3 mass eigenstates, 2 square mass differences are important when we discuss neutrino oscillation probability. Okay. Now, there are many ways, at least another 2 ways of writing this probability by using the fact that this is a unitary matrix. But we will find it on the notes, because there is no physical insight that we can derive from all these ways of writing the oscillation probability. This is the formula, and obviously it depends on the 3 mixing angles and also on the phase delta, because there is this complex conjugation. Okay, maybe the best way to proceed to have some feeling of what this formula implies is to consider 2 flavor neutrino oscillation. So imagine that you have only 2 flavors. So imagine to have only nu e, nu mu as flavor eigenstates, nu 1 and nu 2 the mass eigenstates. Obviously this formula will simplify, okay? And so, for instance, the p nu e nu mu is 2. Just, okay, in the two-flavor case, the mixing matrix is cos theta sine theta minus sine theta cos theta. So unitary two-dimensional mixing matrix depends only on one parameter, no complex phase. So the star does nothing. And if you write minus 2 u e2 u mu 2 u mu 1, it can be calculated, it's not difficult to see that the two-flavor case gives sine squared 2 theta sine squared delta m squared L over 4e. So this is our final formula. The one formula that everyone remembers. Since we have no complex phase, this is simple to evaluate, and only one mixing angle. So this is just a number. If you know the mixing, this is the amplitude of the oscillations. So for theta equal to 0, this is 0, there is no mixing. While for theta equal to pi over 4, the mixing is maximal, and this factor is equal to 1. When we say oscillations, you see, this is also a number that we must know from experiments. Oscillations for fixed energy, oscillation in L, or for fixed L, if you detect neutrino at distance L from the production point, you will see oscillation in energy if there is a spectrum of initial neutrinos. Here, however, the unity, so if you want to put numbers, you decide to measure, for instance, delta m squared in electron volt squared, L, for instance, in kilometers, and E in GeV. So if you do this, so we measure delta m squared in electron volt squared. Length in kilometers and energy in GeV. We have here EV squared, kilometers, and GeV. So let's say 10 to the 6 to 9 EeV. You see that here you have EeV times kilometers, so energy times distance, and you can divide again by 1, because this is 1, and you will get this factor here. There is also a 4. If you see, this is 1.27. So if you measure delta m squared in electron volt squared, length in kilometers and energy in distance, or equivalently length in meters and energy in MeV, the numerical factor that you have to put here is 1.27, okay? And this allows, remember that the period of sine squared is not 2 pi but it is pi. So you see that the oscillation length is pi divided by delta m squared L over 4E, okay? And so this factor is useful when you want to compute the oscillation length. In the case of two neutrino oscillations, obviously, because the formula for 3 generations contains sine, cosine of the mixing angles, and also you have to compute the exponential that contain sine and cosine. And as you will see on the notes, there are formulas more explicit than this one on the blackboard to have also an idea of oscillation in 3 generations. But this formula allows us to understand that the mixing will give the amplitude of the oscillation, and the delta m squared will give the oscillation length, okay, depending inversely on the delta m squared. By the way, I called delta m squared the only delta m squared that survives into oscillation, so the 1, 2. Okay, I think we can stop here for a coffee. Maybe you need probably more than me. Okay. So, I write again here, P nu E to, let's say, E mu, just to mean the nu E going into a nu mu as sine squared 2 theta sine squared delta m squared L over 4E. For instance, if you have many cycles, and this will give an average. For instance, if you are measuring neutrino with a given spectrum at a fixed distance, and this phase is large, this will give 1/2, for instance. So when we talk about averaged oscillations, this means that delta m squared L over 4E is much larger than 1. And since in general the energy of neutrino is not known exactly, or experiments have a finite resolution, this will give 1/2 in the case of many oscillation cycles. Or you can expand this if the argument of the sine squared is much less than 1. So there are many cases in which you can do different approximation from a probability, especially in the 3 neutrino case. For instance, we know that the delta m squared 1, 3 is much larger than the delta m squared 1, 2, or can be much larger, let's say this way. And so we have one scale given, but one mass difference, mass squared difference, much larger than the other. There are approximations for the oscillation probabilities, but I will not give you the formulas you will find on the notes. Now, we will return to the oscillation parameters, and we will see, we will discuss the mixing angles and the neutrino mass square differences at length in the following. But before turning to the measurements that constrains all these parameters in the oscillation formula, let's see what happens when neutrinos propagate in matter. Okay. Now, here, let's distinguish two cases: constant matter density or varying matter density. Obviously, the first case is simpler. So imagine you have matter with constant density, and neutrinos can interact with the electrons, protons, and neutrons that are in matter. And at the beginning, we saw that if the neutrino energy is not so high, neutrino absorption can be neglected, and there is a phenomenon similar to the refraction index for the light when it propagates in a medium with different from the vacuum, for instance in water. This happens also for neutrino, and the calculations can be done for what is called forward coherent scattering. This means that neutrinos don't see every, for instance, electron in matter as a separate target, but all the electrons in the medium as one target. And the cross-section get enhanced by a factor depending on the electron density. Okay. Let's say, a sketch of the proof is on the notes, but here just I want to report what is the result. So if you consider the all the flavors, the effect of matter in constant density matter on neutrino propagation is to add to the Hamiltonian a new term, interaction term. I call it vu alpha, that is V CC delta alpha E plus V and C. That is exactly square root of 2 GF and E delta alpha E minus 1/2 n small n. So let's see what this is. In general, all flavors can scatter, for instance, a nucleon, and we have neutral charge interaction that we saw yesterday. But only electron neutrinos can do charge current scattering with the electron in the medium. We saw that charge scattering transforms a neutrino into an electron, for instance. And so you start with nu E, E, and you end up to nu E, E. Obviously, you have also neutral current interaction with a Z, nu E, electron, electron, but also a proton of a neutron or a neutron, proton and neutron. And this is true also for muon and tau neutrinos. So we have one term that you see is there for all flavors, and one term that depends on the charge scattering that is there only for electron neutrinos. So this is the potential that you must add to the Hamiltonian, and it is diagonal in the flavor basis. So if you consider this as a matrix, V, so you have, when alpha is equal to E, square root of 2, GF, and E minus 1/2 NN. But by the way, sorry, this is the electron density, so number of electrons per centimeter cube, and this is the number of nucleons, okay? And here you have, when alpha is not equal to E, you have only the second term. Okay. The proof of this fact must be done by taking the Hamiltonian density that we wrote yesterday, depending on the, sorry, there is a parenthesis here, and here there is GF. You have to take the Hamiltonian density and make an average over the electron fields, okay? But what matters is the result. So an additional potential that you have to add to the Hamiltonian. But now we face this problem. This potential is diagonal in the flavor basis, while the propagation is diagonal in the mass basis. So we must combine the two results to get the oscillation probability in the constant matter density case, okay? So this is coherent forward elastic scattering. Elastic means the initial state is equal to the final state. So neutrino have the same momentum before and after scattering. If not, you will not have coherence, okay? So it's like, as I was saying, a refracting index for the neutrino propagation in the matter. Now, the answer in the end will be easy, but what we should do is the following. So imagine to start with the new alpha T, or L, as I was saying, T and L. So with this state, we consider the state that at T equal to 0, or L equal to 0, is a new alpha. So imagine to have a neutrino state that initially at T equals 0 at the production point is a new alpha, and then evolves in time. And your Schrödinger equation is, let's say, H nu alpha. And we can write it as the free Hamiltonian plus the interaction Hamiltonian, nu alpha T. Okay, the free Hamiltonian in the mass basis is diagonal. So this is in the mass. While Hi is simply this matrix is V. But this is in the flavor. basis. Now, what we should do, but I will not do all the steps, mathematical steps, but just sketch what we are doing, is to consider the amplitude alpha beta as the projection on the flavor beta of the new alpha at time t. Okay, so actually these are what I called components of flavor states. Remember when I told you that you can write a state as a superposition of flavor states, or, so this is sum over alpha, of mass states. So this is just a different way to call the, here I'm following the Kim and Giunti book, okay, in this notation. Now, as I told you, these components transform with the U matrix, while states transform with U star, the complex conjugate. Now, with some step, and you always insert the identity to prove these steps, you can see that the final equation is this one, dx. To simplify the notation, for instance, consider beta equal to E. So, sorry, let's say this is the initial state. So define A alpha as the alpha A alpha E A alpha mu and A alpha tau. So this was the initial state, and we forget the second index because we put all in a vector, okay? Consider this as a column vector. The equation, evolution equation for A alpha is, let's see, the final result is 1 over 2e u m u dagger plus matrix A that we define as 2 square root of 2 gf e times ne 0 0 0 0 0 0 0 0. So, what this means? What should we do to evaluate how these components evolves? We should write an Schrödinger-like equations and use the same basis for the two Hamiltonians. So we transform this into the mass states. This is diagonal, while this needs to be rotated to act on the mass states. If you remember, the potential had a term on the diagonal equal for all flavors, and this can be taken out because this will give an equal phase in the evolution of all flavors. And when we consider the oscillation probability, the modulus square, this gives 1. Okay, so the common part in the matrix V that we considered before can be neglected. The only part that matters is the difference that is in the first term only for electron neutrino due to the charge current. Okay. This is the reason why this matrix A has this structure. Only electron neutrino can have charge current, and so we neglect the part of the matrix that is proportional to the identity, because in the oscillation, if we have the identity or something that is proportional to the identity, this gives a common phase to all states, and we can neglect that. Okay, so in principle, the neutrino electron the electron density, can depend on x, on the distance, but here we are assuming constant density. This is for this part here. So see, now this is in the flavor basis. What is this? Here, M, this matrix M, actually is defined in this way. M is 0, 0, 0, 0, delta m squared to 1, delta m squared 3, 1, 0, 0, 0. So if we are in the vacuum, we can neglect the matter potential, so sorry, you hear me? The matter potential. Here, imagine the mass eigenstates, this is the mass matrix. Also here, we have taken out something proportional to the identity. So we saw that the oscillation probability depends on the mass square differences, okay? So imagine that you take out m1 squared. This is 0 now. Here it appears the square mass m2 squared minus m1, and here m3 squared minus m1. So this structure depends on the fact that with 3 states, mass eigenstates, we have 2 mass differences, only 2. If the propagation, if we consider the mass eigenstate propagation, the Hamiltonian is diagonal. But we are looking at flavor eigenstate propagation. So there is a rotation to go from mass to flavor, and since for the components the flavor components are related to the mass components by the U matrix, if you want to go from flavor to mass, you have U dagger. So you, from the mass eigenstates you go to, sorry, from the flavor you go to the mass, then there is the diagonal evolution of the mass eigenstates, and then you go back to the flavor states, another U. So this term comes from the, let's say, non-diagonal evolution of neutrino flavor eigenstates. So the evolution is diagonal in the mass, but since we are now studying the flavor components, we go from flavor to mass, diagonal evolution, and back from mass to flavor eigenstates. This energy into the denominator was the energy that we have also in the two flavor oscillation, delta m squared L over 2E. And if you take out as a common factor the E will appear also here, okay? The potential depends on GF and NE, but if you take in evidence a common factor into the denominator, the energy will appear also here, okay? So this is the reason why the Hamiltonian in the flavor basis has a diagonal term that is non-zero only for electron neutrinos, plus a non-diagonal term, because in mass the Hamiltonian is diagonal, but not in flavor, and so the U matrix appears. Okay, this is the final formula and the interpretation of the final formula. Starting from here and taking the derivative, you have to insert twice the identity and get this, okay? But we are interested only in the final formula. Now, let's see, what happens if we solve this equation? Now this matrix is not diagonal, but we can diagonalize it. So if you compute this matrix here and again take out something that is proportional to the identity, this is, let's say, the flavor Hamiltonian, all this. You can write the flavor Hamiltonian as 1 over 4e, obviously also this is in the Hamiltonian, minus delta m squared. Oh, sorry, this is in 3 generations. Let's see what happened in 2 generations, because in 3 generations it can be done, the diagonalization, but formulas are very, very complicated. So only in 2 generations we have, sorry, cos 2 theta plus a, let's call this term here a charge current, ACC, delta m squared sine 2 theta, delta m squared sine 2 theta, delta m squared cos 2 theta minus ACC. Okay, so this was the flavor Hamiltonian in 3 generations. To simplify things, let's consider 2 generations, and we know that. Are you okay? So, in 2 generations, this mixing matrix is real and depends only on 1 parameters. If you do calculation of this, just you take this rotation matrix, cosine theta, sine theta, you do this product. This m now is 0 delta m squared, only 1 delta m squared. You add this 2-dimensional, and you subtract something that is proportional to the identity. You end up with this matrix. So a 2-by-2 matrix, depending on the mixing angle, the 1 mixing angle that defines u, theta, 1 delta m squared, and this potential for neutrino. The fact that this appears here depends on the subtraction that we have done to the part of the matrix proportional to the identity, okay? So there is this minus here. Now you can diagonalize this, okay? You can find the eigenvalues and the eigenvectors, so the matrix that diagonalize, and the matrix that diagonalize this Hamiltonian is a unitary 2x2 matrix, so it depends on one mixing angle that we called theta m, and so cos theta m sinus theta m minus sinus theta m cos theta m, and this is so that um hf u to the minus 1 m is equal to a diagonal matrix, and the eigenvalues, so the elements on the diagonal, are minus delta m squared and plus delta m squared in matter, and the formulas are the following. So delta m squared in matter is equal to square root of delta m squared cos 2 theta minus acc squared plus delta m squared sine 2 theta squared, and tangent 2 theta m equal to tangent 2 theta divided by 1 minus acc divided delta m squared cos theta. Don't worry that we will discuss what this means, or better if we write sine and cosine. Sine 2 theta divided square root of cos 2 theta minus acc divided delta m squared all squared plus sine squared 2 theta, and the cosine 2 theta m equal to cos 2 theta minus acc delta m squared, and the same square root. Okay. Now, first you understand why we didn't study the 3 neutrino generator case. Because imagine you have the eigenvalues of the HF, when you diagonalize, will depend on 3 mixing angles, the phases, so it's very complicated. And so this is done. It is possible to calculate, to evaluate analytically, but very complicated. So we consider the 2 flavor case. This is a matrix. Okay. What we are doing? We have the evolution of these components, but with some matrix that is not diagonal, and we want to diagonalize it. If we the matrix was the one written up there. If we diagonalize that, we find the eigenvalues, so the mass eigenstates in matter that are characterized by a new delta m squared in matter, because only the squared mass difference matters for oscillation. So with two flavors, you have only one mass square difference. The matrix that will diagonalize the Hamiltonian depends on one angle. That is the new mixing angle in matter. And these are the formulas that defines this angle. Okay. Actually, you need two of these to understand the sign of sine and cosine. From this one only, you cannot. And the mixing angle in matter will depend on the mixing angle in the vacuum and on the squared mass difference, delta m squared, and on the potential, so the electron density in matter. Now, the problem from one non-diagonal evolution has turned in a diagonal evolution. So if we go from the flavor eigenstates or the mass eigenstates in vacuum to through this matrix U to the mass eigenstate in matter, this will evolve simply with the phase e to the minus I the delta m square, depending on this new quantity here. And to go back to the flavor eigenstates, we use the relation that diagonalized the Hamiltonian. Now, the UM matrix will relate the states in the vacuum with the states, the eigenstates in the matter. Okay, so despite the formula looking complicated, actually we have turned the problem of the propagation in matter exactly as we were doing with the propagation in vacuum in something that is diagonal, so easy to calculate. And then we can go back to see what happened for the flavors eigenstate. If you consider the oscillation formula in this can be proven in more rigorous way, but remember that we have in vacuum the P E mu probability was sine squared 2 theta sine squared delta m squared L over 4e. The meaning of all this is that now, for constant matter, we will have P E mu sine squared 2 theta m sine squared delta m squared in matter L over 4e. So the same formula holding for vacuum oscillation holds for in two generations, holds for matter oscillations. All you have to do is take to the HF U dagger plus A divided to E, diagonalize, evaluate the eigenvalues, the delta m squared, and put into the vacuum formula. The mixing angle will be given by this formula here. This is, so what appears to be complicated actually is very simple. When you will have time to think about it, you will see that we are doing a very simple things, but formulas hide what is simple in something that looks complicated because we have to write a lot of square root of. Okay. Obviously, if you consider 3 generations, someone or maybe Mathematica, can evaluate the eigenvalues of that matrix and the eigenvectors. Because U, the matrix diagonalizing the Hamiltonian, will have the columns that are the eigenvectors corresponding to the eigenvalues, as usual. So, but the same formula holding for the vacuum oscillation will hold for matter oscillation if we replace the vacuum angles with the matter angles. But the expression for these angles is complicated. And the delta m squared with the matter delta m squared. Okay, now let's do just one consideration, because for instance, if okay, this is a consistency check. When A, the matter potential, ACC, is 0, this is 0, this is 1, the matter mixing angle is equal to the vacuum mixing angle. Fine. When ACC divided delta m squared cos, maybe I was wrong, this is a 2, sorry, cos 2 theta is around 1. I forgot to tell you one thing. This was for neutrinos. For antineutrinos, the potential changes sign. Okay. Sorry. And all the formulas that we have, one formula in 3 generations for the vacuum oscillation, for antineutrinos, you change U with U star. Okay. So we talk always about neutrino. For antineutrinos, the potential changes sign. So it depends if you're considering neutrinos or antineutrinos, because for neutrinos, given the mixing angle in the vacuum, ACC is positive, for antineutrino is negative. So this condition can be true for neutrinos or for antineutrinos, not at the same time for neutrinos and antineutrinos. When this is true, this goes to 0, and tangent of 2 theta m goes to infinity. This means that this goes to pi over 2, and theta m goes to pi over 4. And when if you look at the oscillation probability, if the mixing angle is pi over 4, this is pi over 2, the sign is 1. So you have maximal oscillation probability. So when this condition is met, you have a resonance. The mixing angle in vacuum can be also small, very small. And if the mixing is small, the oscillation amplitude is small. Okay, so even though the mixing angle in vacuum could be small, if the resonance condition is met, the mixing angle in matter tends to pi over 4, and the oscillation amplitude is maximal, tends to 1. Okay, and this was the reason why this resonance case was thought to be important for solar neutrinos in the early years of neutrino oscillations, because it could help to explain why the flux of solar neutrinos was less, the observed one was less than expected, okay, even for small mixing angle. So the resonant condition gives maximal mixing in matter. but this condition can be true for neutrinos or for antineutrinos, depending on the sign of the cos 2 theta and the potential. Okay? Thank you. Okay, do you have any question about? No. Okay, now we up here, what we can do? We can put an x here. So what if we consider varying matter profile? So the density, the electron density changes in the neutrino propagation. We have done, okay, here is a derivative, and we have obtained this formula for constant matter potential. If this is not true, there will be additional terms in this, and let's write the result. Okay, now to obtain this equation, we change the basis. We go from flavor to matter basis, and imagine to do this basis change here. You will have a new matrix, and when you take the derivative, now you have to consider the possibility that also U changes. And the result is that the equation is this one. I d over dx A E matter, A E mu matter is equal to 1 over 4E minus delta m squared m delta m squared m minus 4I e d theta m dx a e e m a e mu m, and here minus 4I e d theta m over dx. So when the matter profile is constant, this is not changing in x, does not depend on x, and these are the matter components that, when the off-diagonal terms are equal to 0, evolve, as we have seen, in a diagonal way, with the delta m squared in matter calculated as before. Now, these matter eigenstates will depend on the point of the path of the neutrino. And if the change of the electron neutrino density is low, this off-diagonal term would be small, and the propagation, the evolution of these matter amplitudes will be similar, so will be like the constant density case and slowly changing. And we will call this evolution adiabatic evolution. So it's like that you, in every, okay, maybe we will continue this discussion tomorrow is very simple, not so difficult. We're nearly there for the oscillation probabilities in vacuum and in matter. We will start from here tomorrow. Okay? Thank you.